Okay. Please.
Well, good afternoon. Yesterday we talked about how to plot with R, and we saw that there are two kinds of plotting functions: the high-level plotting functions and the low-level plotting functions. So we need to use a high-level plotting function in order to open a new device, and then we can add things to that plot with the low-level plotting functions. The main high-level plotting function was plot, which is a generic function for different methods. And then if we want to add a line, points, etc., we use lines, points, applying text to add a text, or legend to add a legend to a plot, etc. Okay? And there are other high-level plotting functions such as bar plot, pie, hist, etc. Well, I would like to talk now about some functions related to probability distribution, which are quite useful also in R. Well, R has 4 primary functions to work with statistical distributions. Each function has a 1-letter prefix followed by the root name of the distribution we want to work with. So there are 4 types of functions: functions that start with D, functions that start with P, with Q, or with R. So a function that starts with D followed by the root name of a distribution is a function that computes probability mass function in the case of discrete distributions, or the density function in the case of a continuous distribution. A function that starts with P is a function that computes the cumulative distribution function. A function that starts with Q computes quantiles, and a function that starts with R gives us random numbers from the distribution that we want. And then we use this prefix followed by binom if we want a binomial distribution, norm if we want a normal distribution, poise if we want a Poisson distribution, etc. Okay, so we can combine this prefix with the root names here to create, for instance, the function dnorm to compute the probability density function of a normal distribution, or we can also use the function p binom to compute the distribution function of the cumulative distribution function of the binomial distribution, or r univ to generate numbers from the continuous uniform distribution. Okay? And we can use these functions in order to create typical graphs of probability distribution. So for instance, if we want to represent the probability mass function of a binomial distribution, for instance, a binomial with n equal to 20 and p equal 0.3, then we can do like this. So first we define the parameters: n is 20, p is 0.3. Well, this distribution has values from 0 to n. And now I have to compute the probability mass function, and this is P because this is the, D because this is the probability mass function for a discrete distribution. This is the prefix for the binomial distribution. I want to compute the probability mass function in K for a binomial distributions with parameters n and p. So these are the 21 values that I have. I should save this in Y, for instance, and now I can plot K versus Y. Since I want a probability mass function, then the type of line that I'm going to use is H, which is for vertical lines. Okay, so here we have the representation of the probability mass function of a binomial distribution in this case. And if we want a representation of the cumulative distribution function, then instead of d by num, we have to use p by num, because p is for the cumulative distribution function. So y2 is going to be the cumulative distribution function of a binomial distribution evaluated at k with parameters n and p. I can represent plot k versus this y2, and now, since this is a cumulative distribution function, the type is going to be S for steps, okay? And we could do the same for any discrete distribution, just changing the root name for the distribution that we want. And as always, I can change the appearance of this plot with color, with a title, with labels for the axis, etc., as yesterday. And what about a continuous distribution? So it's more or less the same. Suppose that now we want to represent a normal distribution, a standard normal distribution. Well, if I want to represent the density function, then I should generate points x between -3 and 3, for instance, 10 numbers here, and y has to be the density of the normal distribution evaluated at these points. So the density function is d, the prefix for the normal distribution is norm of x, and the next arguments of these functions are the mean and the standard deviation of the normal. And by default, these are 0, 1, so if we want the standard normal distribution, then this is enough. And now I plot x versus y. Well, I should draw a line, so instead of this, the type should be L, because I want a line to represent the normal density. And if I want the normal distribution function, then it's almost the same, but instead of y computed as d norm, I want p, because this is the cumulative distribution function. Norm is the root name for the normal distribution of x, without any other argument, because by default is the 0, 1. And again, the type should be, in this case, a line. Okay? And here I add a main title for these plots, and here I do the same, but I represent different normal densities. So here I create a vector of values between -6 and 6. First, I plot the standard normal density, and then I add a normal with mean 1, which is the second argument. So by default, the standard deviation of this density, which is in red, is 1. So this is a normal 1, 1. This is a normal 0, 1.5. I don't give the mean. It's not necessary if I want the value by default. And here, the second argument corresponds to the mean, and the third argument corresponds to the standard deviation. So this is going to be in blue, a normal with mean -1 and a standard deviation 2. And you have to be careful that I draw the things in this order. If I began with this in blue, and then try to add the other ones, I will have problems with the scale, because the first plot is the one that fixes the scale, okay? So if you want to represent the one in blue first, but you want to have the other ones, then in the plot, in the first plot, you should change xlim, change the limit of the y-axis in order to have the scale that you need to plot more things later, okay? So. Questions? Well, and here I use another function. This R norm generates numbers from a normal distribution. By default, since I don't give any other argument, this is going to be from a normal 0, 1. So what I'm going to do here is to represent an histogram with those numbers and try with a plot a normal density to check that those numbers come for the normal distribution that I wanted. Okay, so first, I generate, for instance, 1,000 numbers from a normal distribution, and then I'm going to plot a histogram with these values. Well, remember from yesterday that by default, these are frequencies, absolute frequencies. So if I want to see here the density of the normal variable, this is not going to work. So I should plot a histogram with frec false. So now this histogram has area equal to 1. And now I can add here, for instance, the density function of a standard normal here, and we see that the numbers that we generate seem to come from a normal distribution, okay? And I also add in the slides the kernel estimation of the density given by the numbers that I generated, okay? And this is done here with lines density xc. These are the numbers that I generated. This is the kernel density estimation, and here I add a line in blue with the kernel estimation, and in red the real density function. So, well, we use a lot these kind of functions, R, D, Q, or P functions to generate numbers from a given distribution, or to compute quantiles from a given distribution, or density or probability mass function depending on continuous or discrete distributions, or to compute cumulative distribution functions of a given distribution. So P, D, Q, and R, and then the root name for the distribution that we want to apply. Well, I'm going to talk a little bit about time series, how to plot the time series in R, although you will have a chapter, I think, dedicated to this point in the second part of the course. So just to give a brief, some comments on how to plot time series. We are going to use first this data set air passengers. We already did this plot, I think. If you remember, this was an object of class TS, which means time series. And if I plot air passengers, this is what we get, okay? Well, there is this other data set in the library time series, and we also worked with it, MSFT, and we also can plot this element. This is also a time series, but the class is different. It's not TS, but time series. Okay? So they are both time series, but they are different. They have different class. TS is an S3 object, and time series is a S4 object. Okay, so it's one example. But I can work with this object in the same way. So I can plot MSFT. Recall that this contained 4 time series, the opening, close, high, and up. It contained open, high, low, close, and volume, so I can plot this time series, and this is what I get by default. So in the same plot, I get its time series, okay, in 5 different plots. Well, I could see them all together in the same plot. This is an option. I'm going to do it just with two series, sorry. So I can plot series high and low, for instance. So I just want to represent these 2 series. By default, we get 2 different plots, well, in the same plot, but 2 different frames. And if I want them to be together, then I can do the same, but here I have an option, which is, or an argument of this function, which is plot point type equal single. By default, this is equal to multiple. Well, and I think this is a problem with RStudio because it has no room to, okay, now. So I can choose between plot type single or by default, and we get 2 different plots. And if you want to ask for help, this is not the plot function that if I want to know more about this argument or some other arguments in order to plot a time series, I should ask for help, not on plot, because this is the generic method, but on plot point time series, which is the object. Well, I don't know now why this doesn't work, but for instance, for TS, plot point TS give us the help file for the method for plotting the objects of class TS. So these are the options for plotting TS objects. Okay, and there should be the same idea for plot point time series, which is the other class of object that we represented. So this is not a plot function, this is something more, is plot point the class. Well, and another thing is that suppose that now we want to represent the high prices and the volume on the same plot, okay? So this is more or less the same. If I do high and volume, by default, I get this, which is nice, okay? And if I want them in the same plot, then I will do high and volume, plot type single. Okay, and we have this, which is also correct, but we have the problem with the scales. And we don't see anything about this time series here. So we can also add different scales in both axes, left and right. And this is what we are going to do now in order to see in the same plot these two time series at different scales. Okay? How can we do that? Well, we can use some of the tools that we talked about yesterday. So first, I'm going to plot one of them, the high one. Plot MSFT high. I represent this one. Okay. If I add now the volume, I'm going to obtain nothing. I mean, I'm going to have the same problem because the scale now is the one that is fixed by this first plot, okay? So what I'm going to do is to use one of the options in this part function that I mentioned yesterday that can set options for the plots. And in particular, I'm going to use the option new equal true. Okay, so this what this does is that it doesn't clean the frame before plotting, okay, before drawing. So I say part new equal true, and then I plot the other one. But if I do this, the new axes are going to be plotted over the old axis. Okay, we can try with this. So you see here in the left that this is not very nice. Okay, so this second plot, we should plot the time series without anything else, without axes, without, okay, and then we add the axis that we want. So I use no annotations here in the second plot, no axes, and if you want a different color to distinguish from the previous one, okay. I plot the first one as it is. I use part new equal true in order to, I don't want to clean the frame before drawing the next plot. I add a plot, but without any annotations, axes, or etc. Just the time series. And now I want to add in the right the axis for this second time series. Okay? And in order to add an axis, here, yesterday, I mentioned this function. This is a low-level plotting function, I want the axis in the right, and this is number 4, 1, 2, 3, 4. Now I have it. And if you want to add something, for instance, I'm going to add here a text to know that in the right I'm representing the volume. So here, in the right, the word volume.
Sorry, I have a silly question. You use this in 46, for example. You have C, parentheses, high, and volume. What is there? I mean, is this a syntax for the command plot or specific of the MSFT?
No, this is, I have this data frame NSFT. This is the data frame, and I can show here how it looks like.
Okay. So you know from the head that's C, so it might have been something. Well.
Yeah, this is, well, I don't know what head. Okay, so this is my data frame. It has these columns, in particular the one with name high and the one with name volume. These are the ones that I want to represent. So I want, in this data frame, I want those columns. So brackets, all rows, and how do I specify these two columns? With a vector with the names volume, comma, high, comma. Okay? So I could do a step here. This is what I want to represent. My dat is this. And now plot my dat. That's it. Well, so this is the way we have in order to have two different scales in the left and the right. We plot the first plot, then we use part new equal true, and we add the second plot without annotations, and then we add axes in the right or text in the right, etc. Okay? Well, and finally, let's talk about how to save plot. Sorry, you have this option here in RStudio to export a plot as a PDF or as PNG, etc. But we can also do it from the script. So I'm going to use the. Here we have. So in order to save a plot or to export the graphic into external file, we have to follow these 3 steps. So first, we have to start the graphics device driver for producing the file. We can use different functions depending on the format we want in the end. So PDF if we want to save as a PDF, or JPEG or PostScripts, etc. So if you want to see the options, you can ask for help devices. Okay, this is the function that controls these things. So we start this graphics device, we then plot whatever we want, and at the end we close the file by typing def.off. Okay, so here we have an example. So for instance, I want to create a JPEG file. So I start the graphic device with the function JPEG and the name of the plot that we want to create. Okay, so my plot 1 with the extension that I want. And here I plot whatever I want. So for instance, plot, I don't know, 1 to 10, 1 to 10, and I can add a point in 2, 3, color red. And now if I finish here, then the point off. Okay. So I compile or run this code, and nothing appears here, but if you go to your workspace, then you should have this file, myplot1, with this plot. I plot this line 1 to 10, 1 to 10, and I add this point here in red. And if I want a PDF, I can do the same. I open the device, I do the plot, and finally I close the file. So when you are writing code, you don't get the plots here. It's better to do something like this. And
may I say to R which are the size? The size, or I don't want this default size, but I want to.
yeah, I think in the par option you have arguments for the width and the height, and I don't know, even in this, here you have if you want to export the graph with a width or a height, or okay. So this is for when you export the file, and if you want to control here the size of the things, I think that this is the function that you have to look for help. I mean, in par you have many parameters that also control the size of the font or these things. And for the file to which you want to export, then help of PDF or help of this one, and also width, height, etc. The background color, etc. Different things. Well, and here I mentioned also that well, I learned about this preparing this material. So R can also generate high-quality vector files with the package Cairo. The idea is the same. This is the package that you have to install and load, and in particular you have, for instance, this Cairo SVG. Open the device, plot, and then close the device, or Cairo PDF, plot, and defof. The idea is the same, but these files have higher quality. Okay? And also allow you to do transparencies of colors and things like that. Well, there are examples if you want to learn more about these things. So maybe this is a better option to export files.
I just installed, and there's a Cairo device also. Is that
No, it's just Cairo. So I think this extension opens with an Internet Explorer. Or yeah, and this you can, oops. Yeah, this has much more quality than the other one. Okay, questions? Well, so we can have, I don't know, 10 minutes or to try with an exercise about plotting, or if you want to try another exercise. So you could try to reproduce this plot. Okay, there are 4 in the same plot with densities and distribution of a beta and a gamma with different parameters and with different colors, legends, etc. Okay. If you have problems with the size of the legend, it's because of the size of this window here. You can it's better if you run the code in R, not in RStudio, but in R, and you won't have problems with the sizes of the things, okay? Or if you save everything to a file with Cairo or with the normal device. So I have written here the first one, and the other ones are exactly the same, but changing D by P for the probability distribution, cumulative distribution, or beta by gamma for the gamma density or gamma distribution. Okay? So can we continue, and then at the end, if you want, we can do more exercises. So now I'm going to talk about how to program with R, how to write our own functions, how to write loops, etc. Well, I think that all of you have experience with programming, with MATLAB or with other programming language, so this is going to be quite easy. So the only thing that is different in R is the syntax, but the other is the same. So R statements mainly consist of expressions to be evaluated, and control flow, as you know, refers to the order in which these instructions or functions calls of a program are executed. So there are different kinds of control flow statements. For instance, executing statements only if some condition is met, or executing a set of statements a given number of times, or a set of statements until some condition is met, etc. Well, so R provides special syntax to use in common program structures. So how do we write a conditional execution in R? And this is the situation. We are here, and then we have a condition. If this condition is true, we want to evaluate these expressions here. If not, then we want to do these expressions number 2, and then we come here and continue with the program, okay? Well, the conditional expressions in R have this syntax. So if parentheses, inside the parentheses, the condition, and this has to be true. This is an expression that has to be true or false. If this is true, then R is going to evaluate the code inside this, I don't know the name in English for these things. And we can end here, but we can also add an else condition. If this is true, then we do this, else we do, otherwise we do this. And we can also put if something, else if something, else if something, else, as always, okay? So for instance, here we have an example. X is this vector, 2, 1, 3, and now if the square root of 9 is greater than 2, then return mean of X, otherwise I want the sum of X. Mean of X, sum of X, okay? Well, we used to write this like this, but maybe here we have problems, I'm not sure. Oops. Okay, if we write the code like this, maybe you have problems because it's it's waiting for something else. You should, if this is inside a function, there is no problem. It can go like this, but if not, then you should put all together into here together, not to have problems with this. Okay, this is just if we don't have this inside a function or inside another environment. So in general, this should work, but not in this case. So okay, so this is the way in which we use the conditional statements in R. There is another option which is quite useful, and this is a vectorized version of the if statement. Okay? And this is the function if else. So let's try with this example. I have a vector and I use this if else function to see that if x is greater than 3, then give me the mean of x, otherwise give me sum of x. And this is a vectorized version because it takes the first component of x. If this component is greater than 3, then compute the means, otherwise the sum. Then it goes to the second component of x. If this is greater than 3, it returns the mean, otherwise the sum, and so on. Okay? So y is a vector in this first case, this is not true, so I get the sum of x. In the second case, the same. The third case, the same. For the fourth component, this is true, so I get the mean, and the sum.
I have a question. If you have a parallel machine or something, does this really parallelize automatically, or do you have to...
You can parallelize with R, and you need RMPI is a package to do parallelization with R. It's also possible, yeah. So we avoid loops, for instance, with these kind of sentences here, if else. Okay. What about the loops in R? Well, so a for loop, well, is the do loop, or will repeat a given code a certain number of times. So it has this syntax: for, and parentheses, a variable, this is the index that we move, in, we have to write in, and here we have to give a vector where we want to move the index, okay? And inside the commands that we want to execute each time. So for instance, bueno. For parentheses, the index is I in 1 to 5, print y, this is 1, 2, 3, 4, 5. Well, I don't need a loop for that, because in R we can have advantage of the vectorized functions, but anyway, this is just an example. And here this index can move in 1 to 5 or in 2, 7, 5. So here I can write a vector using the expressions that we learned to create vectors, sequence, C, or whatever. But in general, we do loops for y in 1 to 100 or... Well, so suppose, for instance, that we want to compute the row sums for a matrix. So I have this matrix here. And I want to sum this row and this row. And if I don't know about the row sums function or the apply function, then I could try to write a loop in order to get this. So for E in one number of rows, and number of rows is given by the dimension of the matrix, the first component of the dimension. I want to compute the sum of the row I of the matrix. And I want to save it in the first component. If I'm with the first row, I want to save this in the first component of a vector that will have the sums of the rows of the matrix, okay? So the thing is that here I need my vector component E equal to this. But then I have to initialize here the vector. And I initialize a vector as numeric. Okay? I cannot create this without defining the vector previously. Okay? If you try this is not going to work. It says this is not known, this is not found. So first I have to create this vector is a numeric. And if you know the length of the vector, then you can say here, this is going to be a numeric with anger components. It's not necessary. You can do like this, but if you know it, then you can write it like this. Okay? So if you write this, my V is by default a vector with 2 zeros, and then this can be done. And here, my V is the row sums, which is the same as row sums of A, which is the same as apply A to the rows, the function sum. Okay? So we can avoid this kind of constructions with this kind of functions. But we have also the option of the loops with R. Well, and we have also another looping structure, which is repeat an expression. The only thing that we have to be careful is that we have to add a break, because this never ends until there is a condition to stop. So here, for instance, x is 7. I repeat printing 7, but also I add x plus 2, until x is greater than 10, and then it breaks and finishes. And also the while loop, while parentheses, the condition, this is going to be the code here is going to be evaluated as long as this condition remains true. So again, we have to be careful that write a condition that ends at some point, okay? So we have if parentheses condition else, for parentheses conditions, or while parentheses condition, more or less is the same structure always, okay? And now, if we want to write our own function, well, we have up to now we have used many built-in functions, plot, summary, sum, etc. There are also thousands of functions contributed by the R community in the packages available, but we can also write our own functions in R. So what is the syntax of a function? Well, we can see an example. So for instance, in R we have these functions which computes the median of the absolute deviations from the median. Okay? So let's see the structure of this function in R. So we write here, when we write a function, the name of a function without parentheses, just the name, we get the code for the function. Well, not always, because for instance, if we want to know how the mean is computed, we get this, which is a use method. We don't see the code behind, but in most cases, we get the code for the functions. Okay, so this is math, and here we see the structure of a function in R. It says function parentheses. Inside the parentheses, the arguments. Some of them have default values, others don't have default values, okay? And then inside we have some code. And in particular in this case, well, this is nothing that I want to mention now, but here we have an if statement, and here we compute the median of the absolute value of x minus the center, and the center is given here as an argument, and by default is with respect to the median. So this is this computes the median of the absolute deviances or differences from the points to the median. Okay, so we will try to write something similar. So let's create our first function. What do we need to write? This is the syntax for writing a function in R. We have to give the function a name and then assign to that name a function, inside the parentheses the arguments, and here the body of the function and the return value with return. Okay? So my first function. I create a function with a name myf1. This is a function. It has only an argument, x, and it computes 2 times x plus 5. And I want to return this value. Okay? So I have this, I run the function, now I have my f1, I have it, and I can use it. My f1 of 5 is 2 times 5 plus 5, which is 15. Okay? In fact, I wouldn't need this return if I do like this. Then the return is not needed, because by default it returns the last thing that you compute. So this is the same. And what about the arguments? Well, I'm going to write, this is my f3, and I don't remember a lot about my MATLAB, but here we can write all functions together in the same script, and tenías que poner el mismo nombre en MATLAB, ¿no? Había que poner el nombre para cada función. Here you can write all the functions together and in the same script, and the script can be, the name has not to be with the names of the functions or... So my f3 is going to be x equal 3. So what happens with this function? This function has a default value. I can execute the function without arguments. So it's going to be evaluated at 3. Or I can evaluate the function at a given number. And functions can have several arguments, so my f4 is a function. We have the argument x by default equal to 3 and y by default equal to 5, and I'm going to compute this plus y plus 5. So my f4 without arguments is 2 times 3 plus 5 plus 5. Or I can also use, for instance, my f4, 4, and this is going to be 2 times 4 plus 5 plus 5. because the first argument is going to be to the x. Or I can do like this, and this is going to be 2 times 4 plus 6 plus 5. Or I can do like this, and if I give the name, then this is 2 times 6 plus 4 plus 5. Okay, so this works the same as with the other functions in R.
I have a question. When you use always the assign, and sometimes you use the equals, could you have defined the function using the equal sign instead of the assign?
Sorry?
Go to line 11, for example.
Yeah.
Upstairs. Okay, so there you put my F4 assign function. Would you have defined it with the equal?
This, I think, oops.
Well, I'm just curious.
This works too also.
Works too.
Yeah, the problem is with the, here you cannot use assign, for instance. And, well, I only had one problem with changing equal from assign. It has to do with the arguments of a function. It was a bit complicated. So, in general, there is no problem. You can use both, but it's true that I'm used to assign the values with the arrow and then use equal for the arguments. In principle, there is no problem, but sometimes, but not in this case. I mean, you can use both. More things. Let's try with my F5. This is a function that, well, I give it a sequence of numbers, and it represents the power function given the power that I want. Okay, so this is going to be a function with 2 arguments, the vector that I want to represent, the power to the one I want, the function. Okay, so this is my function. I'm going to, each time I call my F5, I'm going to represent plot x versus x to the power given by the argument power of x. And I'm going to add a title here, which is, well, I didn't mention this function, which is quite useful. I'm going to pass x to the power of, comma, and the power x. Okay, this is to pass test with a variable. So I have this function, and I'm going to create a sequence of numbers between -10 and 10. And I'm going to use this my F5 to represent x to the power of 2, for instance. Well, I have this problem with the or x to the power of 3 So the first thing is that, of course, I can use functions inside other functions. But the other thing, or what I want to explain with this example, is that what happens now if I want this plot to be in color red, for instance. So then maybe you think, well, then I should here add an argument, color, and then here I know that the plot function has an argument call, and then this should be, for instance, if my argument is called 2, then I should call the plot function with this argument as the color. Is that clear what I want to say? I mean, I want a function that, for instance, uses a plot. And, okay, to a plot I can say a color or axis or the main. So should I write also all these arguments in my function in order to pass the arguments to the other function? And this should be, if I have to do that, it could be a mess, okay? But I don't have to, because in R we have the 3 points argument. Let's call it 3 points argument. Okay? So check the help of the plot function. Help plot. Well, I don't know why this doesn't work right now. If you see here the plot function, it has plot x and y and 3 points. What does this mean? Well, this means that I'm going to plug here every argument which makes sense here. Okay? So in particular, it makes sense for the plot functions to give it a call argument, or give it a type of line argument, or give it whatever. Okay? So the arguments are not defined, are included in these 3 points. And I can do the same with my function. I can define my f5 function with x, with power of x, and with more arguments. And when I call the plot function here, I'm going to call to the plot function with more arguments. Okay? So if I do this argument is going to be here. Well, this is called. You are giving me another argument which is called. And in principle, I don't know what to do with this argument, but I go to the plot function, and here I can try to plug the call argument. And if it makes sense for the plot function to use an argument call, then it's going to be used. And if it doesn't make sense, then it's okay. I'm not going to use that argument. Okay? So if I run this, I have my plot in blue. But I don't need to define my function with all the arguments that another function inside my function is going to need. I don't have to know all the arguments that I'm going to need. I always can put 3 points, and then its argument that is not defined is going to be in this part, and it's going to, the function is going to try to plug the argument inside if it makes sense. Was I clear? Or? So I can call my f5 with a color, with a type of line 2, or with a main. With a main, no, this is already defined. With, I don't know, without access. Axis. Type is not this. Type is L. I think it's access part. Okay.
Then I have a question. suppose that you do two different functions, plot and something else, and they have different arguments. How is R going to figure out which arguments go to one and which ones go to the other? Or is going to assume that whatever makes sense?
Yeah, if I have here, for instance, lines, and I add a lines whatever, the call argument in the 3 points is going to be plugged to plot and to lines.
And if this is incompatible,
No, because, well, the call argument should be only the color. In R, all the functions that are defined and that use a call argument, the call means color. So there should be no interfere, unless you define a call argument in your function, which is not the color, and then maybe you have problems with that. Well, if I want to return more than one element, and this is the example in page 155, here. For instance, I want to return in this function the input and also the output, which is 2 times x plus y plus 5. Well, the return function only admits one object, okay? So I can only return one thing, one object in a function, but the solution to that problem is to use a list, okay? So most of the functions in R return lists. And in this list, I'm going to return my input, x and y, and I'm also going to return the computation that I want to do. Okay, so this is the way in which we return several things in the same function. And here we see the example. So I created this function, and I save the result of this function in out. Out is going to be a list, because this is what I return with my F5 in this example. It has two elements. Input, which is 4 and 6, the input values, and the result, which is, in this case, 19. Well, and of course, we can include loops, if statements, whiles, etc. in our function. This is a simple example. I'm going to do this one. I'm going to create my own function to compute the row sums in a matrix, okay? So my row sums is going to be a function. The argument is going to be a matrix, A, for instance. I'm going to plug here the code that I wrote before. So I'm going to compute first the dimension of A to know how many rows I have to sum. And row is dim of A, the first component. Okay. So for I in 1, 2 number of rows, I'm going to compute the sum of the row I of A. And I'm going to save this in the component Y of a vector. I have to define the vector before, so this is going to be a numeric with this length. And I'm going to return the result of this function is going to be this vector, my V. So I here have the matrix that I always use, and I'm going to compute my row sums of A. And this function does the same as row sums of A, and that's the same as apply A1 sum. Okay? Well, the thing is that they are not exactly the same, and here I suggest how could I study these three functions. Okay? This system time measures the execution time. Okay? So I can compute the execution time of these three functions for a large matrix as this one. I generate a lot of numbers from a normal distribution, and I create a two-column matrix with that, and I want to compute the row sums of this matrix. And I will do it with my function, with apply, and with row sums. And with system time of this execution, I get the execution time for the three functions. And these are the difference. And as you see, the best that you can do, for instance, to sum the rows of a matrix is to use row sums, which is much faster than apply. The apply functions are not especially fast. They are especially useful, but if you have large data sets, maybe it's not the best option. Okay? But it's true that this function only sum, and this can do a lot of other things. Okay? And our function is not that bad also. Okay?
Is it because apply is object-oriented?
Sorry?
Is it because apply is object-oriented?
I don't know. Yeah, but this is something that, for instance, in my case, I didn't learn until I had to run code which was time demanding, and I realized that I was using apply function, and it takes a lot of time. So if you want your code to be fast, then, well, maybe R is not the best choice. And sometimes once you have R, which is quite useful for many things, then some parts of the code, it's better if you write them in Fortran or C, and then you call them within R. But not written in R, but written in other code and called into R. Okay. Well, so I think it's better if we stop now. There are some exercises about writing functions, or yeah, you can try them, and then tomorrow we see regression and optimization with R. Okay. You have, in particular, exercises